Deep inside a secured, windowless operations floor in Boulder, Colorado, federal forecasters monitor a constant stream of solar telemetry. This is the Space Weather Prediction Center. Across walls of displays, analysts watch extreme ultraviolet imaging of the solar disk, tracking plasma density, magnetic flux, and solar wind. They are watching our star, waiting. The entire operation centers on a brutal physical reality. The Earth's magnetosphere, the invisible shield protecting terrestrial biology from ionizing solar radiation, also acts as a massive conductive snare. The same magnetic field that allows our biosphere to exist will amplify an incoming coronal mass ejection and fry our electrical grid. We are protected by the exact physics that will cause our own reset. If you want to track the space weather and historical anomalies that threaten our planet, subscribe to the channel. We decode the physics of the universe. The geometry of our planet's magnetic field is the core of the problem. Generated by a churning dynamo of liquid iron in the Earth's outer core, the magnetosphere extends thousands of miles into space, forming a massive, invisible teardrop that deflects the baseline solar wind. Without it, our atmosphere would simply blow away. But this shield isn't a solid wall. It's an elastic web of magnetic field lines. When a massive blast of magnetized solar plasma, a coronal mass ejection, or CME, slams into the day side of this field, it doesn't just bounce off. It couples. The impact compresses the Earth's magnetic field lines, pushing them toward the night side of the planet. These lines stretch and snap back into place in a process called magnetic reconnection, generating massive, rapidly fluctuating magnetic fields in our upper atmosphere. Thanks to Faraday's law of induction, a fluctuating magnetic field induces an electrical current in any conductor nearby. The magnetosphere catches the solar storm and translates that magnetic energy into raw electricity, beaming it straight into the surface of the Earth. And we built a world completely unprepared for it. We know exactly how this plays out because we have seen it happen. Red Hill, England, September 1st, 1859. Astronomer Richard Carrington was working alone in his private solar observatory. At 11:18 a.m., he was mapping a complex group of immense sunspots. Since pointing an 11-inch telescope directly at the sun would instantly fry a human retina, Carrington used a projection method. He focused the light from the telescope onto a glass plate coated with a pale yellow wash, tracing the dark magnetic knots on the solar photosphere. Suddenly, two patches of blinding white light erupted from the center of the sunspot group. Carrington froze. He initially thought the projection screen had cracked and let in a stray beam of daylight. It hadn't. He was looking at a localized optical emission of million-degree plasma, a massive solar superflare. He bolted from the observatory to find a witness. By the time he returned a minute later, the white patches were already shrinking to pinpoints before fading entirely. Carrington had just documented a superflare, but the secondary threat was already on its way. 17 hours and 40 minutes later, the sky caught fire. Usually, a CME takes 3 or 4 days to cross the 93 million miles of space between the Sun and Earth. But the 1859 anomaly was different. A smaller, slower solar storm had erupted days prior, sweeping the space ahead of it clear of ambient solar wind to create a frictionless vacuum. When Carrington's massive CME erupted, it entered this cleared path and accelerated to immense velocities in a classic astrophysical snowplow effect. When that billion-ton cloud of ionized plasma slammed into the Earth's magnetosphere, the geomagnetic field vibrated violently. Auroras surged across the globe. Curtains of red, green, and purple light were recorded as far south as Cuba, Hawaii, and Colombia. The sky was so bright that gold miners in the Rockies woke up and started making breakfast, thinking it was dawn. Then the physics hit the ground. In 1859, modern infrastructure consisted of a single technology, the global telegraph system. Millions of miles of raw copper wire strung on wooden poles across continents. To an incoming geomagnetic storm, that communication network was just an infinitely long antenna. The fluctuating magnetic field in the upper atmosphere induced massive direct currents into the ground, and telegraph wires absorbed the charge. In offices from Boston to Paris, the hardware began to spark. The paper tape used for incoming Morse code burst into flames. Operators got severe electrical shocks just touching their instruments. Trying to stop the fires, telegraphers disconnected the large chemical batteries used to power the network. The messages kept transmitting. The induction was so intense that the atmospheric current alone was entirely powering the global communication grid. Operators were sending signals between major cities using nothing but the raw electrical bleed-off of a distant star. In 1859, this astrophysical discharge was just a technological anomaly. The world ran on steam engines, coal, and draft animals. The telegraph was a tiny electric footprint in a vast analog civilization. Today, we have taken that footprint and expanded it across every square inch of the planet. By wiring the entire globe, we've turned a routine solar discharge into a massive threat. We don't use isolated telegraph wires anymore. The North American power grid is a continent-spanning web of extra-high voltage transmission lines. We operate millions of miles of heavy copper and steel cables at 345, 500, and 765 kilovolts. These lines connect thousands of custom-built transformers that step voltage up for long-distance travel and down for local use. Without them, water stops pumping, fuel stops refining, and the supply chain collapses entirely. A coronal mass ejection isn't a targeted weapon. It's just plasma and magnetism operating under basic physics. We supplied the exact infrastructure required to turn it against us. We built a machine perfectly engineered to catch a cosmic wave and short-circuit itself. The forecasters at the Space Weather Prediction Center know exactly how vulnerable this makes us. Their eyes stay glued to telemetry from the Deep Space Climate Observatory, positioned at the L1 Lagrange point. L1 is a gravitational sweet spot 1 million miles upstream from Earth, directly between our planet and the Sun. At this orbital node, the gravitational pull of the Sun and the Earth cancel each other out, allowing a satellite to maintain a stationary observation post. It is our planetary tripwire. If a magnetic tsunami matching the 1859 Carrington event erupts from the Sun today, it hits L1 first. The observatory will sample the plasma density and shockwave velocity, instantly beaming that data back to the windowless operations floor in Boulder. The alarms will sound, but our warning time is incredibly short. The data travels at the speed of light arriving in seconds. The billion-ton wall of magnetized plasma, traveling at 3,000 kilometers per second, hits the Earth's magnetosphere just minutes later. If a massive magnetic tsunami breaches L1 today, that incoming telemetry won't just trigger alarms. It will start a countdown, leaving us with mere minutes before the raw physics of a geomagnetic storm start dismantling the North American power grid. The Sun isn't a solid mass, it's a turbulent fluid sphere of electrically charged plasma, which means it doesn't rotate evenly. The solar equator spins much faster than the poles. Over an 11-year cycle, this uneven rotation catches the Sun's internal magnetic field lines and drags them forward, wrapping and twisting them around the star. As these magnetic lines wind tighter, the mechanical tension builds. They become highly buoyant. Eventually, they punch right through the solar surface. We see these areas of intense magnetic distortion as sunspots. But magnetic fields hate tension. They want to rest. When the twisted lines above a complex sunspot group get pushed too close together, the plasma reaches a breaking point. The lines pinch and sever, snapping violently into a simpler shape in a fraction of a second. This is magnetic reconnection. It's the exact same physics that causes auroras here on Earth, but on the Sun, the scale is totally different. The sudden snapping of these massive magnetic bands releases millions of megatons of kinetic energy. The surrounding plasma flash heats to tens of millions of degrees, triggering a solar superflare. This rupture launches a staggered, multi-wave assault on the inner solar system. The first wave is pure electromagnetic radiation. A blinding burst of X-rays and extreme ultraviolet light erupts from the site. Because it travels at the speed of light, it crosses the vacuum of space in exactly 8 minutes and 20 seconds. We get zero advance warning. By the time telescopes at the Space Weather Prediction Center spot the brilliant white flash, the radiation is already hitting the planet. This localized blast of high-energy photons slams right into Earth's dayside, hitting the ionosphere. Under normal conditions, this sensitive upper layer of the atmosphere acts like a planetary mirror. High-frequency radio signals bounce off it, letting transmissions skip over the horizon and span the globe. But the extreme ultraviolet wave from a superflare alters the atmospheric chemistry instantly. The radiation penetrates deep into the ionosphere, stripping electrons from gas molecules and thickening the layer. The planetary mirror instantly becomes a sponge. Instead of bouncing radio waves back to the ground, the supercharged atmosphere absorbs them. Commercial pilots flying oceanic routes suddenly hit complete communication blackouts. Emergency maritime frequencies drop out into unbroken static. At the same time, this influx of solar energy rapidly heats the upper atmosphere, making it physically swell outward into space. Low Earth orbit satellites suddenly find themselves dragging through thicker air, pulling them off their carefully calculated trajectories. Microwave signals beamed down by GPS satellites now have to punch through a swirling, disturbed plasma. The signals scatter. GPS locks degrade or fail completely. That doesn't just mess with navigation. It strips away the exact timestamp precision needed to sync deep-sea oil drilling algorithms, automated port logistics, and global financial transactions. All of this happens within seconds of the visual flash. But space weather forecasters know the X-ray blackout is just the prelude. The light is the muzzle flash. The bullet is still on the way. Trailing behind the radiation is the mass itself, the coronal mass ejection. When those magnetic lines snapped, the recoil scooped up a billion-ton chunk of the sun's outer atmosphere and hurled it outward. Unlike the massless photons of the flare, this expanding plasma cloud has physical weight, density, and its own embedded magnetic field. And it is moving incredibly fast. A standard solar storm might take 3 or 4 days to navigate the ambient solar wind and reach us. A super CME from a Carrington-class event operates under different physics. If earlier, smaller storms have already swept the space between here and the sun clear, the main plasma cloud hits a frictionless vacuum. Accelerating past 3,000 kilometers per second, this wall of magnetized gas closes the 93 million-mile gap to Earth in roughly 15 to 17 hours. The clock is running. Forecasters lock their focus on a single patch of space 1 million miles upstream, the L1 Lagrange point. The Deep Space Climate Observatory, or DSCO-VR, orbits this invisible node. It's humanity's primary solar wind monitor, acting as a cosmic buoy to measure the cresting wave of solar material right before it breaks against Earth. When the CME's shock front slams into DSCO-VR, the satellite's sensors start furiously sampling the plasma. Analysts need 3 critical data points: density, velocity, and internal magnetic orientation. The first 2 dictate the raw kinetic force of the impact. The third determines whether the power grid survives the day. They are looking for the BZ component. Because a coronal mass ejection is a severed loop of the sun's magnetic field, it carries its own internal magnetic polarity. As the cloud travels, this field can point north, south, east, or west. Earth's native magnetic field, the shield that protects our atmosphere, points north on its day side. Magnetic lines pointing in the same direction naturally repel each other. If DSCOVR shows the incoming plasma cloud has a strong northward-pointing field, analysts can breathe. A northward CME will still violently compress the magnetosphere, spark brilliant auroras, and cause a geomagnetic storm. But the 2 magnetic fields will largely slide past each other. The planetary shield holds. But if the telemetry shows a southward-pointing field, the physics flip. Opposites attract. If the billion-ton plasma cloud hits Earth with a south-pointing magnetic field, it doesn't bounce off. It locks on. The southward lines of the solar storm instantly merge with the northward lines of Earth's shield. The invisible barrier peels open, creating a direct conduit between the solar plasma and our atmosphere. Measuring this polarity in real time is messy. As the CME hits L1, it's usually preceded by a solar proton event, a blizzard of high-energy particles accelerated by the shock wave itself. These protons slam into DSCOVR's optical sensors and star trackers. On the cameras, it looks like a blinding snowstorm. The physical impacts of the protons create transient electrical noise deep inside the magnetometers. Data packets drop. Telemetry spikes. Analysts have to filter out the noise to find the true BZ signature hidden in the wave. The readout fluctuates wildly as the turbulent outer edges of the plasma wash over the sensor, north, south, east. Then, As the dense, highly magnetic core of the ejection swallows the satellite, the orientation stabilizes. It drops hard to the south. The field locks. The mass of the storm has just passed the 1 million mile marker. At 3,000 kilometers per second, it will cross the remaining distance in about 15 minutes. The protective magnetosphere is mathematically certain to fail. The solar plasma is about to couple directly with our planetary shielding. Any debate on the operations floor evaporates. The storm won't deflect. It's going to ground out. The only calculation left is the scale of the impending systemic failure. As the most massive astrophysical force humanity has ever recorded bears down on our grid architecture, the focus shifts entirely to the brutal reality of what physically breaks first when a colossal solar payload directly merges with Earth's magnetic field. Telemetry from the L1 Lagrange point leaves no room for debate. The embedded magnetic field of the incoming plasma cloud has dropped hard to the south. Opposites attract. 15 minutes after enveloping the Deep Space Climate Observatory, the billion-ton wall of ionized gas slams into the day side of the Earth's magnetosphere. It does not deflect. The southward magnetic orientation of the solar plasma aligns perfectly with Earth's northward pointing shield. At the magnetopause, the boundary where the solar wind hits, the two magnetic fields splice together. Physicists call this dayside magnetic reconnection, and it peels the invisible shield open. Earth's magnetic lines are dragged backward, stretching tens of thousands of miles into the night side of the planet to form a highly energized tail. The tension builds, the physics stretch to the breaking point. Eventually, these elongated magnetic lines snap. The rebound releases colossal amounts of pent-up kinetic energy, firing a highly charged plasma sheet straight down into Earth's upper atmosphere. The shield is breached. The sky is now coupled to the ground. Faraday's law of induction takes over as the planet's magnetic field violently whips and fluctuates under the sheer kinetic weight of the solar storm. It generates huge electrical currents. Earth is a rotating sphere of conductive minerals and salt water, so these fluctuating atmospheric fields induce a heavy, slow-moving electrical charge deep in the lithosphere. We call these geomagnetically induced currents, or GICs. This is where astrophysics collides with planetary geology. The currents sweeping through the crust don't travel evenly. Bedrock dictates the path. In regions dominated by deep sedimentary basins, the crust is highly conductive. The electrical current easily dissipates through porous, moisture-rich sandstone and shale. The ground swallows the charge. But North America isn't just sedimentary rock. Vast stretches of the continent, the Canadian Shield, the Pacific Northwest, the eastern seaboard, sit on dense, crystalline igneous and metamorphic rock. Granite and gneiss. These older formations are highly resistive. They act like planetary-scale electrical insulators. When the GICs sweep into these regions, the dense bedrock blocks the electricity. The current pools. It builds beneath the surface, desperately searching for the path of least resistance. It can't go down. It has to go up. It seeks metal. For the last century, utility engineers unknowingly built the perfect escape route for this trapped voltage. The North American power grid relies on thousands of extra-high voltage transmission substations. To keep them safe, giant copper grounding mats are buried deep in the soil beneath every major site. These thick mats are wired straight to the neutral points of the transformers sitting above ground. It's a standard engineering protocol. Normally, this Y-grounded configuration acts as a pressure release valve. If lightning strikes a tower or a line shorts out, the excess high-frequency electricity bleeds down the neutral wire and dissipates harmlessly into the earth. During a severe geomagnetic storm, that safety mechanism runs in reverse. The ground stops absorbing voltage and starts pumping gigawatts of unfiltered electrical current upward. The GICs surge out of the resistive granite, push through the buried copper mats, and drive straight up the neutral wires. They bypass traditional circuit breakers entirely. The safety infrastructure becomes the exact vector for systemic failure. The grid is actively pulling a localized stellar discharge directly into its most vital and fragile hardware. Official grid data downplays this vulnerability, but the blind spot is massive. Most extra-high voltage substations lack shielding against this specific type of planetary current. Engineers designed the grid to handle bursts of high-frequency alternating current. They didn't install neutral ground-blocking capacitors to stop a slow, creeping wave of direct current from the sun. The door is wide open. When the GIC enters the neutral wire, it flows straight into custom-built extra high voltage transformers operating at 345, 500, and 765 kilovolts. These are the machines that step voltage up to push power across hundreds of miles and step it down to feed heavily populated cities. Inside these iron leviathans, mechanical breakdown starts instantly. Modern transformers operate strictly on alternating current. In North America, power pulses through the grid in a symmetrical sine wave, reversing direction 60 times a second. The steel core of the transformer easily accommodates this smooth, oscillating magnetic flux, transferring power from the primary copper windings to the secondary ones. But the current entering from the ground is different. Because the solar storm fluctuates so slowly compared to the grid's rapid cycle, the hardware perceives the cosmic current as a steady flow of quasi-direct current. Injecting direct current into an AC transformer instantly corrupts the internal math of the machine. The DC current offsets the magnetic baseline, pushing the perfectly symmetrical sine wave drastically off-center. Engineers call this half-cycle saturation. For precisely half of every electrical cycle, the steel core reaches its absolute maximum capacity to hold magnetic flux. It is completely saturated. It can't hold any more energy. But the grid keeps aggressively pumping megawatt-scale power into the unit at 60 Hz. Because the magnetic flux can no longer be contained within the engineered pathway of the core, it spills outward. Rogue magnetic fields slam into the surrounding components. They penetrate the internal steel framing, the thick copper windings, and the heavy metal walls of the exterior tank, structural components never designed to carry unshielded magnetic flux. As stray magnetic fields wash through the structural steel, they generate massive, localized electrical loops called eddy currents. The friction is immense. The temperature inside the transformer skyrockets. Under normal heavy load, an extra high voltage core hovers around 90 to 100 degrees Celsius. As half-cycle saturation takes hold, localized hotspots on the structural steel spike to 200, then 300, then 400 degrees Celsius in seconds. The core enters rapid thermal runaway. Inside the sealed tank, thick cellulose paper separates the coiled copper windings, preventing the highly energized wires from shorting out. As the interior crosses the 200-degree threshold, that heavy paper insulation chemically degrades. It burns, turning to fragile ash and carbonizing in the intense heat zone. Simultaneously, the thousands of gallons of specialized mineral oil used to bathe and cool the components begins to boil. As the oil superheats, it undergoes rapid thermal cracking, breaking down into highly volatile combustible gases. Ethylene, hydrogen, methane. Pressure inside the steel exterior tank climbs exponentially. Dissolved gas monitors bolted to the substation's trigger, screaming alarms in control rooms hundreds of miles away. But the destruction is already underway. The hardware is tearing itself apart from the inside out. Stripped of their paper insulation and subjected to immense electromagnetic forces, the thick copper windings warp. Heavy metal components melt and fuse into useless slag. In some units, the buildup of volatile gases reaches an ignition point, rupturing the sealed steel tanks and sending plumes of superheated mineral oil and raw flame high into the air. These machines cannot simply be replaced. Extra high voltage transformers aren't standard inventory items stored in a local utility warehouse. They are highly specialized pieces of custom engineering, often weighing upwards of 400 tons. Because of their size, they travel on custom-built multi-axle rail cars. The supply chain required to manufacture a single 500 kilovolt unit spans continents and relies on highly pure grain-oriented electrical steel forged in specialized mills. Even under perfect economic conditions, the lead time to order, build, and deliver a single replacement unit is 12 to 18 months. If a Carrington-class superflare induces enough raw current to simultaneously melt hundreds of these cores across the eastern seaboard, the replacement timeline doesn't stretch to years. It stretches to decades. Forecasters at the Space Weather Prediction Center watch ground magnetometer readings spike across the continent. Grid operators stare at telemetry screens flashing red across multiple regional interconnects. They watch the physics of half-cycle saturation actively vaporize their most irreplaceable hardware. They realize the immense copper grounding mats meant to save the system are currently feeding the fire. The grid can't be insulated. The hardware can't be shielded in real time. The GICs will continue pumping up through the neutral wires for as long as the billion-ton plasma cloud scours Earth's magnetosphere. There is only one mathematically viable defense left to save the transformers. Operators have to manually remove the electrical load. They must deliberately disconnect the copper lines. As core temperatures approach critical melting thresholds, engineers are pushed into a corner. They frantically model the physics of a controlled continent-wide shutdown, wondering if they can sever the transmission corridors and intentionally crash the North American power grid before the hardware permanently turns to slag. The choice is brutal. Execute rolling blackouts within a 30-minute window to decouple the infrastructure, or let the cascading failure trigger decades of catastrophic darkness. The only real way to decouple the grid and save those extra high voltage transformers from melting into slag is to intentionally crash the system. Forecasters and utility engineers have exactly 30 minutes from the moment L1 telemetry confirms a southward magnetic lock to execute rolling blackouts. You have to kill the power to save the power. Inside regional control centers, operators initiate an emergency load shed. Commands shoot through SCADA networks. At substations across the continent, massive mechanical circuit breakers physically open, severing the heavy copper lines from the grid. By breaking the circuit, engineers eliminate the path of least resistance, that massive flow of direct current pumping up from the Earth's bedrock hits a dead end. The current drops, and the extra high voltage transformers cool down before their heavy metal cores can fuse into useless slag. To pull this off, engineers have to deliberately plunge entire metropolitan regions into the dark. Hospitals switch to backup generators, water pressure drops, the financial network fractures. But this engineered, temporary collapse is the absolute limit of our defenses. It's the only way to ensure the grid can actually be rebooted a few days or weeks later, instead of spending a decade locked in a supply chain nightmare waiting for hundreds of 400-ton transformers to be built, shipped, and installed. This 30-minute survival plan relies on one massive assumption. It assumes the 1859 Carrington event is the absolute ceiling of solar violence. It isn't. For over a century, astrophysicists and utility planners modeled their worst-case scenarios entirely on those 1859 telegraph fires and the localized Quebec grid collapse of 1989. These were the modern benchmarks of extreme space weather. But our instruments have only been watching the sun for a tiny fraction of the planet's history. To understand what our star can actually do, scientists had to look past human records and into the biological and geological memory of the Earth itself. In 2012, a team led by physicist Fusa Miyake at Nagoya University started looking at ancient Japanese cedar trees. Trees are basically cosmic clocks. They breathe in atmospheric carbon dioxide, locking the exact chemical makeup of the atmosphere into their annual growth rings. Most of the carbon in our atmosphere is stable carbon-12, but a tiny fraction is the radioactive isotope carbon-14. This specific isotope isn't native to Earth. It's forged by the cosmos. When high-energy cosmic rays and solar protons bombard the planet, they slam into the upper stratosphere, shattering atmospheric atoms and triggering a secondary shower of thermal neutrons. If one of those loose neutrons strikes a stable nitrogen-14 atom, it knocks a proton away. The nitrogen atom transmutes into carbon-14. This radiocarbon oxidizes into carbon dioxide, drifts down into the lower atmosphere, and gets absorbed by living trees. Because the baseline solar wind regulates the amount of cosmic radiation hitting Earth, the carbon-14 trapped in tree rings fluctuates slightly along with the sun's standard 11-year cycle. But when Miyake looked at the cedar rings from the year 774 AD, the numbers didn't make sense. She found a massive spike, a 1.2% jump in carbon-14 in a single year. To put that in perspective, a typical intense solar cycle produces a fluctuation of maybe 0.1%. This ancient surge was more than 10 times the normal planetary background limit. Astrophysicists immediately started looking for local explanations, theorizing a nearby supernova or a massive gamma-ray burst. But data quickly confirmed this hit the entire planet. The exact same 774 AD radiocarbon spike showed up in ancient German oaks and high-altitude bristlecone pines in California. The whole Earth had been bathed in a sudden, overwhelming wave of high-energy radiation. To prove the sun was the culprit, scientists cross-referenced the tree rings with ice core records from Greenland and Antarctica. When extreme solar proton events hit the atmosphere, carbon-14 isn't the only isotope created. The collision also forces oxygen and argon atoms to create beryllium-10 and chlorine-36. Unlike radiocarbon, which drifts as a gas, these heavier isotopes attach to aerosols in the atmosphere. They precipitate out, falling in heavy snows before permanently locking into the ice sheets. Glaciologists drilled deep into Dome Fuji in Antarctica and the Greenland ice sheet, isolating the layers formed precisely in 774 AD. The ice was packed with extreme concentrations of beryllium-10. The dual spikes in radiocarbon and beryllium proved the source wasn't some distant exploding star. It was our own sun. The Earth had taken a direct hit from a colossal solar superflare and proton storm orders of magnitude larger than anything in recorded history. These massive historical anomalies are now known as Miyake events. Further ice core drilling uncovered a whole timeline of them. The 774 AD strike, another massive one in 993 AD, a huge spike in 660 BC, and an unfathomably large event hidden deep in the Holocene epoch dating back to 5259 BC. The discovery of Miyake events completely rewrote the math on planetary risk. The 1859 Carrington event, the benchmark that dictates all our modern grid shielding and emergency shutdown protocols, doesn't even register as a minor fluctuation in the ancient isotopic record. It was a glancing blow, a minor magnetic storm compared to what our sun is actually capable of. If the sun launches a coronal mass ejection on the scale of that 774 AD event, the 30-minute warning from L1 telemetry is entirely useless. Any plan for grid survival evaporates under that scale of magnetic induction. A Miyake-class plasma cloud would compress Earth's dayside magnetosphere so violently that the shield's boundaries would be pushed deep inside the orbits of our geosynchronous satellites. The induced currents forced through the bedrock of the North American eastern seaboard wouldn't measure in the hundreds of amperes. They'd measure in the thousands. The localized ground potential rise would be so intense that the copper grounding mats meant to bleed off excess voltage would instantly become lethal conductors. A voltage spike that large would race up the neutral wires and arc right across the open gaps of the massive gas-insulated circuit breakers. The planetary current would jump the safety mechanisms entirely. Long before human operators could manually shed the load, the intense electromagnetic interference in the atmosphere would scramble the microwave and fiber optic lines connecting the control centers to the substations. The SCADA network would go deaf. The commands to open the breakers would never even arrive. The extra high voltage transformers would instantly hit half-cycle saturation. Their steel cores would dump magnetic flux into their exterior tanks, superheating thousands of gallons of mineral oil in seconds. That cascading thermal runaway would trigger simultaneous, explosive ruptures across the entire continental grid. We built an incredibly fragile, hyper-connected electrical grid directly on top of a resistive geological anvil, all while orbiting an active star capable of planetary-scale magnetic resets. Another extreme geomagnetic event is a mechanical certainty. The differential rotation of the Sun guarantees that a magnetic flux tubes will continue to twist, build immense tension, and eventually snap. Magnetic reconnection is a perpetual, unstoppable process. That kinetic energy will be released, and those billion-ton clouds of highly magnetized plasma will be ejected into space. Astrophysicists don't debate the physics of a catastrophic solar strike anymore. They just debate the timeline. The ice and tree rings prove the Sunfire's Miyake-class blasts on a recurring basis. We just don't know where we sit on that schedule. Every single day, the Earth rotates through space, carrying an infinitely complex, unshielded grid that already operates at the razor's edge of its physical capacity. 1 million miles away, the Deep Space Climate Observatory sits at the L1 node, staring into the blinding white light of the photosphere. It's just waiting for those twisted magnetic bands to snap. When they do, and when that internal magnetic field drops south, humanity will be sitting directly in the firing line, tethered to an infrastructure that is perfectly engineered to catch the wave.